From IIT Bombay, and we'll be talking about the stochastic viscosity conditions.
No, his viscosity solutions to stochastic control problems. Okay, so what I'm going to do is actually it's something continuation with what Professor Ghosh has done, and then see he was concentrating on the same dynamics. So it's a controlled process given by an SDE. And then, so what I am going to do is, what I am going to relax is, I don't assume that it is uniformly elliptic, but I just take it as actually just elliptic. And then, so the problem is very hard. Let's see what we can do. And then, so the problem is very hard. So typically, in the two standard problems in stochastic optimal controls are with infinite horizon. One is a discounted cost problem, which is somewhat easier. What one does here is, so you have a payoff, which is you have a cost, which takes this form. This is Rxt Vt. Using a different notation than what he is doing, and then we have the average cost problem. Oh, this is the expectation with respect to the law of the process when you are initially at x. Is the initial condition. So what one does is actually just look at this SDE with this initial condition. Suppose you have a solution, look at the corresponding distribution, and then you take the average of this process with the under that distribution. So that's the meaning. And then we have the average cost problem or the ergodic. Here what one does is you look at the following cost. You take the time average of the finite horizon cost, and then so the problems are actually just and so here again so these are the controls which already he told us. So this will be, so you are going to minimize either this or this among all possible admissible controls, and then okay, so here so this is what I am going to do, and because results are known only there, and for the ergodic cost problem nothing much is known.
It is ergodic. Why is there an expectation? You are taking it as the average.
Yes, there are some results, but that is in the non-degenerate case where you can avoid this and you can actually optimize in the almost version. That's possible. And I think one of the best reference for all these things is their book. This I don't know the spelling. I will just write Ari and then Borkar Ghosh. Ergodic control of diffusion process is in 2002, 2012. So there they essentially discuss about average, the optimizing this in the average sense and again in the pathway sense, almost sure sense. So is there. Okay, so now the thing is some comments. So here again we are going to take it as suppose you so here again suppose you take Vt as a prescribed control. That means you are given the Brownian motion, you are given the probability space with a Brownian motion on it and control process on it. So make and then you look for a solution of this equation. So then with the standard Lifschitz continuous assumptions, then one can have unique strong solution. Then the question comes about feedback controls. Then so that means controls of this form when you take Vt to be of the form some. Then for non-degenerate, we have seen that it will have a unique weak solution. But suppose when you remove non-degeneracy, then what one can get is actually one can show the existence of a solution. So how do one proceed is what we are telling. So what one does is you perturb this and then make it non-degenerate, and then this is essentially the small noise argument. So this is essentially where the viscosity solution comes.
Take epsilon times identity there and.
Yeah. So what one can do is actually you define this equal to sigma sigma, and then add and then take the square root, and then so it's essentially this is the small noise limit idea or the correspondingly the viscosity solutions. So what one does is actually just take this perturbation, epsilon perturbations, and then it will become non-degenerate. So then even for the feedback, then you will be having unique weak solution. So call it x epsilon, and then so further I will be assuming that they are bounded coefficients. Then one can there is something called a Kolmogorov criterion for tightness. So one can easily prove using this boundedness. So you will be having a tight family of probability measures. And then since it is tight, it will have limit points, and any limit point, then take any limit point, and then what one does need to do is actually one need to look at the corresponding martingale problem, and then pass to the limit, and hence you can show that any limit point of this is going to be solve this SDE. But what one misses here is actually uniqueness. Uniqueness is not there, so one can easily get examples where non-unique solutions are there. But that's not going to affect us much. The reason is that so you start with a admissible control. There may be multiple solutions, but there is a solution. What you can do is actually you just club it with the solution, and then rather than looking at an admissible control and the corresponding cost, what you do is actually an admissible control and take one solution from it and then define the cost and then optimize over all the admissible pairs rather than the admissible controls. So that way one can actually make the problem well defined here. Okay, but still the average cost problem is.
So the solution which you are getting x, Vx, the x is solution is the limit of this epsilon solution?
Yes.
Is not any other solution?
No.
So you can have other solutions also, right?
It can have, yeah, that I don't know. But anyway it has multiple solutions. Even in this sense there are multiple solutions.
In this sense, multiple solutions, but there may exist solution which lies outside these limits.
Possible, I don't know.
For example, in the deterministic case in the conservation laws or Jacobi,
then
epsilon limit is unique, okay, but there are many outside solutions.
Yeah, so that
they need not come from the.
yeah. So here, so it is true. So you take sigma to be 0.
Therefore, you are taking only those limits away.
Yes. Yeah.
You don't infer over all the solutions.
That's a control problem. So the control problem is actually you try to find out an optimal control where the cost is minimized. Okay. So the problem is minimize J alpha x v dot over all admissible controls. So this is the problem.
But you take only one particular solution.
Here.
You take only.
No. You take all. Yeah. No. You take all of all the limits you will be taking into account. Yes. Yeah. Only from that. 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 No. That we are not doing.
It can lead to a different problem altogether.
Yeah. Yeah. That we are not doing. No. That's true.
So given a v, you identify x to be the limit of this epsilon going to zero, that limit.
Exactly.
And the problem is posed there.
Okay. So now, so this is the idea is essentially going to be this. So that's naturally why the viscosity solutions are going to come. Okay. So now the main ingredient is again. So when you take sigma to be 0, then what you are going to get is actually the deterministic control problem. You take sigma equal to 0, you get recover what Shaijo has done, but for the different cost. Okay. And now, so what I will be doing today is actually I will just blindly write down the corresponding Hamilton-Jacobi-Bellman equation for this. So that's going to be okay. I'll make one more comment. So here, what is L phi of xv is coming from the generator. So it's going to be 1 by 2. And here I am so there is one difference in notation I am using. So here I am taking small v from capital V, and what is the capital V? I am just using the relaxed control setup. So V is actually going to be P of u, all the probability measures on the actions set U, and then and here again so B is coming from another function B bar, which is the average over. So what is this B? B is going to be, so it's for probability measure, so is integral over for x belongs to Rd and V in V is the. So similarly you will be defining R, all the, it's completely in the relaxed setup. Okay, so all the assumptions we will be making here. So V will be Lifschitz in X and it will be continuous, jointly continuous, and B bar will be bounded. I am going to straight away assume boundedness, and the Lifschitz continuous in X uniformly in U, and similarly for B, and then sigma prime is non-negative. Okay, so that is the assumption.
In this equation, suppose you discretize time. T naught plus delta, T naught plus 2 delta. Each subinterval, suppose you use piecewise constant control or something. Yeah, then we get a solution. Now in the limit, we get lot of quantities, right? So,
What quantity?
suppose you take limit. So for each delta you fix, then you have a solution. Whatever Markov chain you have. Now can you consider a limit of these quantities in any way?
So you are only discretizing the time or not the state?
Time only. Only
I
time.
am not sure. They may be possible, but see, there is something called a Kushner's Markov chain approximation is there. One can do that.
Because then also you will get limit points. And the limiting trajectories.
Yeah.
So whether it is something like this.
That again, see that again this non-degenerate, one can easily do the things, but with the degeneracy there will be problems in passing to the limit.
Because what I am saying is that there is a positional differential games. they have the work there. They in deterministic differential games, they do this time discretization. Each interval piecewise constant control, for example, consider the associated trajectory. Then you have Euler-Scauli theorem and go to limit points. So they call it as motion. So the trajectory, as you are telling, is not unique. So then over all possible trajectories, you take minimum. Then you take minimum. This idea is similar, I think. But I don't know the limiting points. That way you get, this way you get. Whether same, I don't know.
Check. Yeah, that is something that may be useful.
So you take the discrete.
Huh?
We don't even have uniqueness in law.
No.
If you have uniqueness in law, then nothing. The expectation is taken. So
Then it will not be a problem. So the problem is basically there is no uniqueness.
In any sense.
Yeah. So so that's the way even the JB part for this is almost a complete theory is there, but there is no satisfactory verification theorem is not there. See, the problem is actually suppose there is a viscosity solution, some weak form solution is there, then what one expects is actually one need to find out the optimal control. The natural thing to do is actually you take a minimizing selector, then that's going to be somewhat a Markov control. Then you plug in there, you have multiple solutions, and then even how do you show that it is going to be optimal? That is difficult, that's not known. Okay, so the equation is this. With this generator comes from the SDE. Now, as one see that you put sigma equal to 0, then a special case of you get the first order PDE, and then so there is a need for viscosity solution. So what one want is actually how the way one need to. So and we are essentially talking about actually the good solutions. So what one is going to do is actually this perturb this and then pass to the limit. So this perturbation essentially will make you have a uniform convergence. That corresponding perturbed if generator is denoted by L epsilon, and one can see that L epsilon will converge as well uniformly on compact sets. And then so what you need is actually to get the good solution, you need some sort of a stability. If further you know that there is a corresponding solutions which converges uniformly, then if one can show that limit is again a solution, then that's what someone expects. So you need a solution which is stable, which satisfies some type of stability, and the right thing is actually the viscosity solutions. Okay, so that is what one will be doing. Okay, so what I will do is actually now I will just for some time we will be just looking at not the HJB really. So what I will just change the notation, otherwise I will be deviating from the standard subsolution and super solution. The reason is actually here we generally use this, and then PD you generally use minus. So all the subsolution and super solution things will get go the other way. But all the viscosity solution I only see minus there. So I am just going to use that notation. Okay, so I will define. Let me just write down. I need a minus here. I think that is the reason you are using supremum, isn't it?
Yes, I was using supremum.
I am not using that. I will put the minus outside.
Okay.
And then I will be having this this. Okay, and then so what one is going to do is actually I am going to look at a PDE, and then I will look for a solution for this equation and keeping in mind that my f is this. So that's my f. But here it is equation is in Rn. So start with an open set which is, so first we will try to define a viscosity solution for this second order PDE. So what one need is actually some ellipticity one need. So you cannot choose any f, but with some conditions on this f. So what conditions we will be using the following. You need to impose that the corresponding equation is elliptic, and then so one is f is continuous jointly in all the variables. Second is f is elliptic. So what you need is so for q which is less than or equal to q prime, that means q prime minus q is non-negative definite. Then for any x fixed xup, this will be and then what you need is actually a monotonicity in the u variable, so that is increasing. So this assumptions we will be making, and then we will start the definition. So it's the same definition is exactly the same what Shaiju has done. Yeah, this is the one.
Because of the 80
Because of this, I think they should have used the other way, isn't it? This is a bit, yeah. This gives you this type of questions, yeah. So yeah, that's the reason we generally use this, but PDE, no, at least Leon's the viscosity solution. This is the standard. All the books is using this, so I'm just following that.
What I have done is bodies terminology.
What is it? Is it they use? Yeah, because you are using there again. So what you have done is actually you had a plus here with a sup and minus inside, isn't it? It's the same notation you are using. Okay, so now the definition is exactly the same. So we are not going beyond the continuous solutions. So you say that a continuous function in O is a viscosity subsolution to 1 if for each x in O and P belongs to C2 of O satisfying what is that? Such that U minus phi has a local maximum at x, then zero and yeah, or see I'm just but that one can avoid, just translate it, isn't it?
Either you must put px or ux is equal to px in the definition.
It is phi x, isn't it? Oh, okay.
There are two things.
Yeah, I know, yeah.
Either the definition put ux is equal to px
I will do that.
or
this should be u, isn't it? Because
No, then you have to put that u minus v vanishes at the point x.
Better we put a phi.
is the test function. Okay.
Put phi everywhere.
Okay.
Yeah.
Okay. And then super solution one defines in a similar way. It should be u, isn't it?
U, but you have to take the definition that u minus v vanishes at the point x.
V is the maximum.
That means the maximum value is
No, but u is the solution.
Yes.
But it's not C.
This function is phi.
actually maximum value of u minus phi.
Yeah, if if there is no ambiguity, if you assume that they coincide at the point x.
In that case, no problem.
Yeah.
If it doesn't coincide, then there
Yeah, I think I'll come back to that. I just when we do something, let's see whether it is correct. Okay, and
C2.
yeah, this is fine.
P is in C2.
About this. This definitely it is d phi and d square phi. Yeah. Okay. So now super solution is actually the same thing. So what you do is actually just super solution. Look at instead of local maximum, it will be the local minimum, and then it's a reversed inequality. And so u is going to be a viscosity solution if it is both sub and super. Okay. So now what one can see is actually there is an equivalent definition one can give, and the motivation behind that is, so you start with a subsolution, and then so that means suppose u minus phi as a local maximum at x, then what one get is u of x minus u of y minus phi of y will be less than or equal to, u of x minus phi of x, then y is in a neighborhood of x, and then so this will imply that u of y will be less than or equal to u of x, then plus, and use the Taylor series, you will get this will become and then so that means it's not going to it's not going to do wrong. We have this right. So that means what you will get is actually u y minus u of x minus divided by this will be less than or equal to 0. So what one can use is actually, so nothing special about actually this d phi and d square phi. So what one can do is actually look at those variables which are p and some q, where p will be a vector and this is going to be a non-negative definite symmetric matrix, and if instead of this, if this is satisfied, and then replace these two with the corresponding thing, it should be satisfied. Then the question is actually that be u.
must take the value. I mean, if you suppose you take, I can always replace u p by q plus some constant.
Yeah, so phi is the test function here.
Yes.
I think you can put u and phi, whatever you want.
Phi I can see, phi I can always replace with, I can translate it and
Ux.
it is ux. If it is phi, then what will be my other definition?
No, you can put a u only when you assume that the maximum value of u minus phi is 0. Otherwise, then only ux
You
not
got
equal
the
to
point, isn't it?
No,
Go ahead with it.
Yeah, yeah. Let's see. Yeah, so that we will see that. So this is actually going to give you another without using this test function, but you use actually some subdifferentials and super differentials, or call it actually that semi jets to give an equivalent definition for the viscosity solution. I will remove this, so this is always assumed. So to do that, so what one does is you define the jets. So for a continuous function, you don't need continuity, but we are not going beyond that. So what you do is actually collect all p comma q such that that is satisfied. So all pq, so that this is satisfied, you call it superjet of u at x, and similarly in O. This you can avoid. The same thing, but the liminf. So for the other one, you get the exactly the opposite thing. Okay, so now, so what we have seen is actually from this calculation, what we have seen is actually only one part. So what one can do now is actually to make it really the another characterizing definition for viscosity solution. Need to do a little bit more. So what one have is actually this lemma. This is nothing but all such that u minus phi has a local maximum at x and where phi is in C2. And what we have done is actually, so we have done what? Yeah, so what we have done is actually we have shown that this is sitting inside this. So what you need is actually the other way. So that means, so this is done using Taylor series, and what you need is actually the reverse inequality. So you start with an element from the jet, and then what you need is actually one need to construct a phi which is C2, and then this is going to be, the differentials are actually going to be this. Okay. So So I will just tell you what I will only sketch. You can so what you do. So you are fixing your x, which is in O. So what you can do is actually just first keep a R ball which is sitting in O, and then you restrict there, and then on this R ball you define the function f of y using that. So it is uy minus ux minus p dot y minus x the positive part of it this is whenever y is here and y not equal to x, and when y is x it is 0. Then since PQ is here, one can show that the only problem is continuity at the point x, and one can easily show that using this. Since PQ is here, one can show that the lim sup of Fy when y go to x will be 0, and so that will make the limit to be 0. So f is continuous using this in 0. Then what you do is actually then define another function Ry. I'll take R naught, R0. So this is R0. This will be this one. Then what you can see is, so H0 will be 0 and H is increasing and continuous. So now again one more thing. So now you define eta r to be some r. So this is just some scaling because you need some desired property which is not. When you see it, then you will realize why this root 3. So you need to construct a C2 function, and so here, so you will be defining up to further restrict. So now what you can see is in C2 of this bond. Further you can see that this is important, 0, and you need to essentially recover this square. So that is why that's scaling. So now the function is ready. Now my function is going to be So now, so this is clearly, so this is C2, and then now one can easily see that because derivatives are 0 here. So you will see that and then see we are not losing anything by this bond. So what you can do is actually you can restrict further, and then you can easily extend to in a C2 fashion to the whole of that is necessary anyway, not necessary. And then so this phi is actually going to act as the corresponding test function. So that will prove this equivalence. So now I think I will remove this.
In the notation of the supergeometric surface, so what is this 2 plus going on? I mean, is there any special significance of the number 2?
Second derivative. These are second order differentials. Okay, so with this phi, so it's clear now I am not.
But why u minus p is the local minimum?
You will be using this, and because h of y, h of r is actually the supremum, and this is just tailor made. So what one need is actually you need that. Just okay. So that will give you this equivalence. So now you have the definition. So now the equivalent definition is going to be so U is the viscosity subsolution if f of x ux and similarly will
Need ux, not ux. Okay.
so that so I will correct it.
U is correct. I know.
So now what I will do is yeah. Oh. Okay. So now important property will do. So that see why I am doing this is actually so to prove the comparison principle I am going to use this. So essentially using that Ishi's lemma, and so there is where I need this. So wherever useful I am going to use that definition which is proper for the analysis. So that
In the first derivative case, if it is non-differentiable, at least one of them has to be empty.
the same things are here. Yeah. So I can list those. See, some properties are actually this are going to be convex, but for the first order then you have closeness, but here it will not be. And then the next thing is actually see if suppose p comma q are actually going to be here, then if any q prime which is bigger than q, then it has to be there. Yeah, because of convexity or the ellipticity. Ellipticity it will be. So that means either it is empty or it has to be infinity. The set cannot be finite. Either it is either empty or it will be having infinitely many elements. And now if both the sub and superjets are actually non-empty, then they have to be same, and then and they will be singleton, and you will get the differentiability. So that properties are there. Okay. Now, what the theorem is, the stability, which is here what is, so you look at a family of PDEs. So that means you take Fn and F with n greater than or equal to 1, and we are going to assume that are continuous and proper. Proper in the sense when you have that monotonicity and ellipticity put together, we will be calling it proper. So now suppose Un belongs to C and you are only going to look at in an open ball. Is a viscosity solution to Fn equal to 0 such that Fn converges uniformly to F on compact sets and so Un converges to U uniformly on compact sets, then U is going to be a viscosity solution. To F equal to 0. See, generally we use viscosity solution as a tool. See, one advantage here, see, suppose when, see where it is really useful is actually when you don't have gradient estimates. If you have gradient estimate, then you don't need this. When you don't have gradient estimates, then if somehow you can prove uniform convergence, then this will help. I think that was the initial thing, isn't it? Then it have gone much far beyond. Okay. So how do one do this? Okay, so this one more thing I forgot to tell. So in the here the definition we are taking something like a local maximum. This one can make it without any loss of generality. You can make it strict. And no need of local maximum. One can even talk about a global maximum. Those things are easy. So you will be using that. So, so to prove that it's a viscosity solution, what I am going to use is the first definition. So what I do is actually you just fix a point x in O, and then I start with something which has a strict local maximum. That will be easier. So let and u minus phi has a strict local max at x. So then what one can see immediately is this. What is that? So ux minus phi of x is a supremum over some ball containing the point x, and which is going to be strictly bigger than the value on the boundary because of the strictness, and this we will be using. Then just give the sketch. Then what one does is, so now you look at the closed ball, and then look at your, look at un minus phi, and look at, so they are continuous, so you have the supremum attained will be some un xn minus phi xn. Then what one need is actually one need to argue that it's a local maximum. So what need is somehow for large n at least xn should lie in the interior. To do that we will be using this. So to do that what one can do is actually, so xn's are here. So here xn will be in Bn, B closure. So take a limit point, call it x hat, and then what one does? Then argue that this will be equal to, and one can argue that x hat is going to be a local maximum for u minus phi, and because it's the strict, this has to be x, and x is in the interior, so you have xn in the interior. So that's the method. Okay, and then so once they are in the interior, then you can use the definition for viscosity solution. So write down. So what you will get is xn un xn which is less than or equal to 0. Now pass to the limit. You can do it because you have even though you have double sequence here, since you have uniform convergence, you can pass to the limit and you will get this. So that means it's a viscosity substitution and do the same thing. Okay. Now, so I think this is the viscosity part I need for the general thing. Now we will go to our so recall our equation. RD. Okay, so I will tell you the approach what I am going to do. So what I will do is actually first I will define the value function, which is the infimum over all d dot of the values of the cos, this is alpha. Then what one does is one will be using the dynamic programming principle, which is given by plus e power minus alpha tau b of x tau for so what we only need is actually this. So for all tau which are hitting times of open ball, and this again is the same as what he has told. So what one, the idea of the proof is, so what one does is actually you just start from here, you take your tau and then split it into 0 to tau, the cost plus tau to infinity, and then you make a translation, translate the time part, and that is really where the difficulties comes. You will be doing this, plus tau to infinity e power minus alpha t r of xt vt. Then what you do is actually you do this. So you have t minus tau comes here. So what you will be doing is actually you just start with a control and then look at the solution till the time tau, and then what you will do is actually you start with that initial condition x tau, and then you take an epsilon optimal here, you take that v epsilon here, and then patch this two processes at this time point, and then use that. So what you can do is actually by doing that, this can be replaced with this plus an epsilon, and then pass to the limit. So that you get one way, and other way is easy. Other way, so you will get one way inequality, and the other way inequality is much easier than with the same idea. It's the same thing. So that is where all the problems come. So you will be using the feedback control. So when you are doing this patching at the random time, so it will make so you have to work in the feedback strategies. Okay, so
here infimum is in the class of feedback.
Feedback controls, but feedback and relaxed, always relaxed.
Feedback in the relaxed.
So we need to use the relaxed because you see you can without the loss of generality you can take all the feedback controls, because all the feedback controls can be written so all the admissible controls can be written as a feedback control. There you need the relaxed. So that's, see, the way you define there, the relaxed form is this. You take an admissible control and then you do this. I will be taking V rather than U. Conditioned on the information up to T given by the process. So here, this is in the relaxed framework. So all the things, but see, but the thing is actually one need to be little bit careful there. See, you are talking about a tau, but that tau need to be a stopping time with respect to the filtration generated by X, isn't it? So that is something very generic, isn't it? So if you to remove that ambiguity, what you do is actually take tau to be the infimum of the time it hits some bond, so that will be removed. But you can work with the other one. But one need to be careful about actually the stopping time being with respect to which filtration. Yeah, see, the prescribed there is absolutely no problem, because the filtration you are always taking with that of the Brownian motion. So here you don't know that.
But in general, is it true?
It is true. Yeah. I didn't argue that. Yeah, this is simple to argue. No, it is true. See, all these things are there in Borker's book, Borker-Ghosh hypothesis. Okay. Yeah, I think now I will be using this, and then so what my idea now is actually use this and show that if V is a continuous, if additionally I know that V is continuous, the value function is continuous, then one can easily argue using the dynamic programming principle that it's going to be a viscosity solution, but under the additional assumption that V is continuous. Then I will be introduce the Ishi's lemma and then prove the comparison result, and hence I will be having uniqueness provided I know that the value function is continuous. Then one can directly show that it is not just continuous, it will be Holder continuous. Okay.
So you haven't considered the time stationary average.
No, that is not known. No, is not. So nothing is known about the solution. See, I don't. No one expect in general, I don't think that one can expect anything there for the ergodic case. See, the reason is actually, suppose there are two, see, invariant measure can be non-unique. So there is a rho there, that rho itself can be a function. It is not going to be in general, there is no reason to believe that it will be a constant. It will not be a constant. But if you have something like a unique attractor type of thing, then there is some hope, but nothing is known.